Okay, off we go. Looks like the recording's working. A real quick reminder, don't forget about the attendance quiz, attendance code. There you go. Okay, so, right, so this is where we left off. We were talking about curl. Now, specifically, we were talking about three-dimensional curl. Remember, this formula we wrote down is in R3 specifically. Right? And we have this interpretation that it's, this is the first picture everybody sees. It's the way you think about curls, it's a way of getting your hands on the extent to which and around what axis the fluid has a kind of a rotational aspect to it. We saw a couple of examples, and I think this is a particularly important one, that it's not about individual particles in the fluid. This example here, they're all moving in straight lines, right? That's not what we're measuring. It's just not what we're measuring. What we're measuring is something different, and the way you would detect that, the way you would visualize that in this context, looks like it's, oh, you know what? That's going to kill the recording. Here, let me pause. Hang on. Okay, so we're recording again. All right, I'll splice these two together before I post, which I think I can do. I'll try. Okay, so the way you would visualize what we're calling curl here has nothing to do with individual particles within the fluid. It's about, imagine that you were to put a small but not infinitesimal object like a leaf in there. And would that leaf be rotating? And again, as we discussed, in this case, it really would. It'd be kind of rotating clockwise, right? Which again is, think about your right hand, point your thumb in the direction of this computed curl, and look at the fingers of your right hand, and you see they're, as seen from above anyway, rotating around clockwise. Okay. All right, so that's what we did last time. Picking up from there now, this three-dimensional curl has a two-dimensional analog. Here's the formula for it. And you'll notice we're going to use the same notation curl here. It is also something that you can shorthand with an operator. And where previously we had put the cross product, notational sloppiness, kind of math slang, if you will. Easy way to memorize the formula. That's kind of nice. Here, instead, the wedge product that we saw back in the same section where we talked about the cross product, in fact. The wedge product is the thing that kind of analogously, it's not exactly the same, but somewhat analogously works in the same position. So that is, in this course, really just kind of a notational observation. Don't overthink this, right? But it is kind of convenient and kind of elegant. Okay. All right, so again, what does this curl represent? Again, it represents, loosely speaking, circulation. Okay, so it's just a two-dimensional version of the same thing. Okay, now here's where I'm going to have to do some pretty serious hand-waving. This is not in the book. This is a little bit of foreshadowing, but I think really important foreshadowing. I think this is certainly when we get to chapters 6 and 7, this is going to be a really big deal and really useful. So I just want to, while we're planting thoughts, right? All this discussion of divergence and curl is just kind of planting thoughts, getting you to kind of, stew on some of these ideas. If you choose to take the gradient operator, let's think about what gradient does. It takes in functions and it spits out vector fields. And then if you take the curl operator, this is all in 3 dimensions, by the way. That takes in a vector field, spits out a vector field. And then if you take the divergence operator, that takes in vector fields and spits out scalar valued functions. If you compose them in exactly this order that I have here, seemingly arbitrarily, amazing things happen. Shockingly convenient, shockingly consistent patterns and relationships just start showing up. Now, why does this happen? Turns out there's it's a really deep question. Why those patterns start to show up was not really fully understood by mathematicians until less than 100 years ago. It's fairly recent math. I can't remember if I've said this before, but the mathematician who figured this out, I am 2 degrees of separation from that guy. Like, my grandfather met him. Like, they collaborated. I mean, so it's really recent, right? Very recent math. Very sophisticated math. So that we're not going to be able to talk about. The way I'm going to present this in this course is to just kind of show you the resulting patterns, which I think are very valuable from a computational standpoint. I mean, when it comes time for y'all to actually use these ideas in an engineering or a physics context or what have you, being aware of the many patterns and analogies and consistencies is a big help, tremendous help. So that I am going to do. So I'm just going to present this here as being a neat pattern. I'm going to show you one thing that's neat about it. Just to kind of segue into it, let me start with a couple of equations. This is easily checked right here. The curl of a gradient is always 0. Now let me go up to the diagram and show you what this means. If you have some function here, and this says if you compute the gradient of that, and then this says if you compute the curl of that, this result that you get will be the 0 vector field. Now, the way I like to describe this in the diagram context, I mean, here, this is an equation that you can write down, and that's great. Here, I'm going to call this a lifetime of sorts. It's just a metaphor. Don't take it seriously. In my little metaphor, every time you take one step to the right in the diagram, think of that as the passage of 1 unit of time. And what happened in this little story? Well, we had some function. And then, time passed. Again, metaphor. You have a vector field. Some more time passes, and you get 0. And I like to think of 0 as being death. It's just a metaphor. Don't overthink it. For one thing, 0, no matter what you do to it, still 0. It's kind of like death in a way. Okay, here's another one. Let's look at, let's see here, I've already forgotten what colors I used. But let's look at, well, you know what, let me just do another one up here. If you have a vector field there, if you take its curl and you take its divergence, you will get 0. So again, lifetime of 2. The 3 stages of the lifetime, I like to think of as birth, survival, death. Okay, again, it's just a metaphor. Okay, now it goes the other way as well. As follows: if you have a vector field, and if you compute the divergence and you get 0, let's speculate on what's the life story that we see part of here. Got a vector field and died here. Remember, all lifetimes have to be 2. We have written here, all lifetimes are 2, which means if this was death, then this must have been the survival, which means it must have been born here. Which means, said differently, that vector field that I started with, this vector field whose divergence is 0, that vector field must be the curl of some other vector field. Now, you can write all these things down, and that's what I have here. Right, so if the divergence is 0, then it must be a curl. Okay. So you can write these down individually, one at a time, as various theorems. And that's fine and probably a good idea anyway. It's a matter of procedure, but the neat little memory trick that I think makes all of these easy to remember is all lifetimes are 2. Consistently. Everywhere on the diagram in every sense. With certain regularity conditions. You've got to worry about continuity and differentiability. That's not what we're here for. Okay, so neat fact. By the way, this is the first step toward this large diagram that I have here on the screen now. And by the way, this diagram is in the Course Resources folder. So if you go to the course webpage, right, go to the course webpage and click on Course Resources and, Course Materials. That's what it is. Go to the Course Materials folder, and there's just a bunch of PDF files in there on this diagram. This is a diagram that I kind of threw together myself. It is a kind of a boiling down, stripping away all the formality and notation that we're not going to be using in this course, and just the bare bones as pertains to Math219. What do you need to notice the powerful patterns in question? I think this diagram does it. And you're going to notice we got these operators in the order that we just discussed. And then down here we have what I have called the lifetime theorems, and you see each one of these is a statement about lifetime being 2. The little notation I'm using is the solid lines represent a hypothesis. So, if you're looking at a gradient, and then the dotted lines represent your conclusion, then the curl must be 0. Okay. And likewise on down the line. So anyway, cool stuff happens when you compose these operators in this order. And more cool stuff will happen. I'm going to keep track of all the cool stuff that happens once we get to chapter 6 and 7. I'm going to keep track of it on this diagram. Everything we do, we're going to kind of report back to the diagram and just talk about what that looks like on the diagram. You're going to start noticing patterns. It's bookkeeping for your understanding of ideas. Let the diagram do your bookkeeping for you. Keeps everything sort of straight in your mind. Okay. Obviously, we have a lot to develop. We don't even know what that means yet. We don't know what that means yet. We don't know what this means. There's a lot of stuff we've got to do to build up to this. So don't get intimidated by the unfamiliar stuff. Okay. Alrighty. So moving along. Some computations. So we've talked about divergence. We've talked about curl. And we've previously talked about how if you have some complicated construction you want to crank out, sometimes it's a lot easier in spherical coordinates. So I'm talking about the Laplacian, right? We wrote down this thing called the Laplacian, and the spherical Laplacian was this great big monstrous thing that was really easy to compute with in some very common scenarios. So we're going to do the same thing now for divergence and curl. And I'm going to show you how to actually do some of these computations to justify they're not as bad as the spherical Laplacian is a monster. Right? These are pretty doable. At least the polar divergence that I'm about to show you. Okay, so starting off, a couple of flashbacks. You may recall we wrote down these formulas when we were talking about the chain rule. You can flip back in the notes to there if you'd like, but these are just sort of statements of the chain rule, reworked around a little bit to solve for the x and y partials. So make sure you look back and recall that. By the way, you don't need to memorize these equations, right? I don't have them memorized. I don't think most people would. And then this right here. Now this we made a reference to these back in chapter 1. And this is just, polar standard basis vectors, and the idea is if you're wherever you might happen to be, if you look in the direction where only r is increasing and theta is constant, well, then this is the direction to go. And likewise for theta here. Okay. And these are just little geometry problems to persuade yourselves that those are what those vectors are. Notice, not constant. Right? These have variables in them. In particular, these are both functions of theta. Okay. All right. Okay, so with all of this established, let's take our del operator. Now again, another flashback. Remember the del operator is kind of think of it as kind of a sort of a vector, it's a vector of operators. It's d by dx in the first position, d by dy in the second position. And here I'm just writing that with standard basis vectors for kind of, it's going to end up being very helpful in just a moment. This is really just d by dx, comma d by dy. Okay, so with that said, I can turn that into that as follows. I hat E1, the first rectangular standard basis vector, you can solve for here like so. D by dx, oh, there it is. And I just put that right there. I didn't really do anything yet. I'm just plugging in, right? I mean, that's what I hat is. That's what d by dx is. I'm just sort of recopying that formula for del. And then likewise for the j hat, and likewise for the d by dy. So this step right here is nothing more than plugging in. And then multiply it out. Collect terms. Really no particularly tricky curves on that. You just sort of write it down and collect the terms. And what you find is that now we have what you might call a polar del operator. This is what the del operator looks like entirely in terms of polar standard basis vectors, polar variables, and polar partials. And very handy in many circumstances. This is a good formula to make sure you have memorized. This is a good formula to make sure that you know exists and know where to find it. I don't particularly advise memorizing. Okay. Alrighty. That wasn't that bad. Right. Next one, kind of an extension. Suppose you have a vector field, and here you go. This is how we write vector fields. Most of the time we write them like this, right? But if you wanted to expand that out in terms of standard basis vectors, there you go. F1 and F2 are functions of x and y. So this is your vector field. Okay, well here's the thing. In the same way that any field vector can be written kind of in rectangular coordinates, namely as a combination of rectangular standard basis vectors, well, I could do it in polar coordinates too. Same field vectors, just write them, in terms of the polar standard basis vectors. And these coefficients, likewise, right, these are functions of the polar coordinates. So those will be in terms of r's and thetas, just rewriting everything in terms of polar coordinates. How you do that is a matter of some algebra, whatever. Sometimes it's actually pretty straightforward. But anyway, the point is this is something you could do. And it turns out, I know this seems like a lot of trouble, but it turns out very often this is much nicer than that is. Surprisingly often. Okay, so with that said, let's think about what divergence would look like. Now, divergence, of course, we already have a formula for divergence. Divergence is del dot F. And notice that's all I've got here. This thing here on the left, this big mess there in polar coordinate. Well, that's literally the del operator that we just derived. That's just that del operator. And, and this is just our polar rewrite of our given vector field. So, yeah, no tricky curves. Okay, having done that, here is another calculation. Now, this one is, it's a bit of trouble. It's not that bad. It's quite doable, but it's more than I want to sort of write all down here in lecture notes. But notice, you just kind of have to sort of crank this out. You've just got to, one at a time, take these operator terms and apply them one at a time to these sort of receiving terms, right? And so, for example, among other things, you're going to have to do this operator on that term. And let's just kind of think it through. No big deal here, but I've got a polar standard basis vector. Okay, it's not good. Sits there. And I've got this 1 over r. All right, it's just sitting there for the moment. Now I've got to take a theta partial of this product. And the tricky part that's easy to forget is ER, non-constant. Easy to lose track of that. But ER, again, going back to here it is. ER is not a constant. It depends on theta. So the theta partial, when you get around to taking the theta partial of that ER, not zero. So what we have here, in fact, this theta partial of that right there, that is actually a product. So you're going to have to use the product rule as you take the theta partial of this product, and it's exactly the same product rule you think it is. You just got to write out those two terms. And then likewise for all the rest of this, right? So you have to kind of FOIL out the whole dot product, and each derivative you have is may or may not be a product rule situation. You multiply the whole thing out, collect it all together, and this is the answer you get right here. So I actually made an exam question of this back in the recent spring, and I just thought I'd show y'all that question. I'm not going to go through this, but I just wanted to make a quick reference. And by the way, for the record, this was a hard exam question, so full acknowledgement. This was a hard question, right? The first two parts are pretty straightforward. But notice this is just a little bit of practice playing with viewing a vector field in polar coordinates and dealing with this formula for divergence, which is in terms of the polar representation of your vector field. So the first thing I had students do was to just rewrite. So here we have a rectangular expression for the vector field. And notice I can rewrite it in terms of polar pretty easily. Now, just a quick reference, which one of these do you think looks like it'd be easier to deal with? This rectangular version, well, I've got polynomials in the denominator, which, we can deal with that, I guess. But it's all else being equal, it's not my favorite. Polar representation. One of the coefficients is 0. Love it when that happens. Right? And this one's not so bad. Then students compute the divergence, and look how easy that divergence computation ends up being because everything's in polar. This was 0 in the first place, so that second term is ultra easy. And then this first term goes down pretty easy too, just not that much to it. So very easy calculation in polar coordinates. Now here's where the question gets hard. I ask students to derive this formula. And so this is the part that's hard, right? And it's doable, but it's a little hard for an exam question. Whoops, wrong button. All it is asking students to do this calculation. So what I want to encourage y'all to do, give this a try on your own first. Give it an honest try. Right? Talk through some of the interpretations of some of the parts of it. And then if you get stuck, you've got this as a backup, right? And you can see I've got my del, and we've got our polar representation of the vector field. You kind of FOIL it out there, and then just, it is a little bit annoying that sometimes I've got to, some of it gets a little troublesome, right? But it's not that bad. If you look at the whole calculation all at once, it's a little overwhelming. But if you look at any individual part of this, it's not that big a deal. For example, let's look at that. Now just quick pause, right? Don't let it overwhelm you. Take a deep breath if you have to, whatever. This says, look at the ER and take the partial with respect to R. I don't know if y'all recall, but we just looked at the formula for ER. It didn't have any R's in it. It only depends on theta. Boop, 0. That's all we're talking about. Take it in little pieces. Be nice and organized, right? Notice I laid things out sort of carefully on the page. You don't want to be dealing with a disorganized mess. That's how you get lost, right? One little bit at a time. It's not that bad. And turns out to be exactly what we wanted. So you've got this as a reference. If you get stuck, give it a try on your own first. No problem if you need to look at the reference. But I do think it's worth giving it a try. Okay, so now you can do something similar with curl. This is the formula. Again, don't memorize these. I don't think, I've never memorized them. I made it all the way through a physics major and a math major without ever memorizing these formulas. I used them, for sure, right? But never memorized them. So don't do that. Likewise, you can do this kind of stuff in 3 dimensions for spherical coordinates. And again, very handy, right? And just as for example, here's your 3-dimensional spherical divergence formula. And you'll notice I'm using the physics convention for spherical coordinates here, because I found this formula in a physics reference. And that's how they like to do it. So, and just as a reminder, you do have to be comfortable using either, it's not just 2 of them, but whatever the notational convention might be that you're dealing with, you got to make sure you're comfortable with. Okay, so again, don't memorize it. This one's enough trouble. I don't even particularly recommend you try proving it. Not that it's not mathematically any harder than the 2-dimensional polar one that we just talked through. Mathematically, they're morally equivalent. There's just a lot more tedium in this one, and so it's not worth your trouble. Okay. All right. So, moving along. That finishes chapter 3. We're going to move on to chapter 5. Oh, hey, wait a minute. What happened to chapter 4? We're kind of skipping over chapter 4 here. Where's chapter 4? Yeah, we are going to do chapter 4. We're going to do it at the very end of the course. And there's a reason for this. The reason is that chapter 6 and 7 are sort of our culminating, that's the big stuff that we want to get to. Ideally, we'd like to get to chapter 6 and 7 as soon as possible. The sooner we get to chapter 6 and 7, the more time you'll have to digest it. And it's a big bite. It takes some chewing, and you need a little time to swallow, and there's a lot to it, right? So we want to get to chapter 6 and 7 as soon as possible. If it weren't for the fact that it wouldn't make any sense, I would start the course with chapter 6 and 7. But you can't, because chapter 6 and 7 will make lots of use of chapter 5 stuff. And they make lots of use of chapter 3 and lots of use of chapter 2 and chapter 1. Everything earlier, all the earlier chapters really are kind of needed for chapter 6 and 7, except for chapter 4. So I delayed chapter 4 to the end of the course. That allows me to start 6 and 7 just a little bit earlier. And so be it. Okay, all right, so back into chapter 5. I hope you all remember we did partial derivatives in chapter 2. It was the very first kind of derivative we talked about in chapter 2. And I gave you an apology and a warning. This isn't really the best way to think about multivariable derivatives. We start with it because it's an easy way to get one into the win column. It's familiar. It's kind of nice in certain ways. But ultimately, we saw a much better way to talk about multivariable derivative. The derivative matrix, much better. Much more natural. Right? Derivative matrices, quick reminder, it's a relationship between input changes and output changes. Input changes are vectors. Output changes are vectors. The relationship between them, the derivative matrix. Partial derivatives are this special case, assuming unrealistically that everything else is a constant. Strange, but very ultimately convenient. Okay? But again, when you look back on this course in 10 years, And you know, if I could pick one thing for y'all to remember about how to think about multivariable derivatives, is that it's the relationship between input changes and output changes as related by derivative matrices. That's really the most important take. Okay, so something's analogous is going to happen here. We're going to start with a point of view that is convenient, but when we're looking back on this, it's really not the right way to do it. All right, so full warning, right? Don't hang your hat on what you're about to see. This is just a kind of get the ball rolling, and we're going to make you, this is not wasted time. We are going to make use of, just like with partial derivatives are very handy, right? Computationally, you got to have partial derivatives, no doubt. And likewise, what we're about to do here is going to be very handy. You're going to need it for sure. It's just not the best point of view in the big picture. Okay, y'all remember all of this. This is just how-to example application of single variable integrals, and that is if you have some area, and if you take that area and you rotate it around the x-axis to produce a volume, and if you want to compute that volume, well, the way we compute that volume is by saying, well, I can look at one little bit of that volume at a time, and that one little bit of volume is going to be a cross-sectional area, cross-sectional area times a thickness. You know, whatever that thickness is, and that thickness is just dx, delta x, depending on how you think about it. Flashbacks, right, everybody? Cool. So area times thickness gives you little pieces of volume, and you just add up all those little pieces of volume, you get an integral, and they call this like volumes of rotation or something. Again, old news. Okay, so fine, good stuff. We're basically going to copycat that now to make our first venture into kind of multivariable integrals. You'll recall that single variable integrals, among other things, will tell you the area under a graph curve. Here, we're going to look at a graph surface. And instead of asking for the area under the curve, we're going to look for the volume under that surface. Is that cool? Everybody see the question? Everybody see how this is kind of analogous in some sense anyway? So, seems like a reasonable first question to ask. And here's the copycat portion. Just like we did in the above example, I'm going to say, well, look at these slices. These slices have volumes, and really all I want to do to get the whole volume is to just add up all the little slices of volume. I like to think of this as like a loaf of bread. The volume of the entire loaf is the sum of the volumes of the slices. And then here's where we kind of feel like we reach a stumbling block. Here's my cross-sectional area. Let me do this with purple again. Here's my cross-sectional area. And I would like to multiply that just like I did up here. I want to take my cross-sectional area and multiply by thickness. And my problem is that this cross-sectional area is not a garden variety high school geometry formula like this was. Right here, I can say, yeah, pi r squared is it's a circle or a disk. It's a disk, and disks are easy areas. Pi r squared problem, and then off we go. Here, that's a weird shape. It's not a rectangle. It's not a triangle. It's not a disk. It's not a thing that we saw in high school geometry class. And so, this is why they don't continue with this calculation in single variable calculus classes. But here's what we can do, and it's really ultimately a pretty straightforward computation. This area that I'm looking for, let's see here, I'll do it in blue. That area, well, it is the area under a curve, isn't it? It's the area under a curve, that curve being a cross-section of our original surface, that surface being a graph. And that allows us to reinterpret what this area is. Area under a curve, sure, but this curve gives me height z as a function of how far I go in that direction, otherwise known as x. I have height as a function of x. That's a graph. And as we see on the next page here, this area that we're trying to compute, that's the area under a graph. Now let's be a little bit careful about this. Y is fixed, right? We're looking for a fixed value of y. It is specifically for one at a time value of y that I want to know, hey, for that y, what's the corresponding cross-sectional area? So I treat y as a constant while I'm computing this area because that y is kind of the premise of the question. Right, it's for that one value of y at a time that I want to know what this area is. So y to be thought of as a constant there, and therefore to be thought of as a constant there, and therefore my integrand here is just a function of only x. Yeah, is that cool? So no big deal. It's totally doable. It's a little strange, a little counterintuitive. You see x's and y's, and you're like, but that's two variables. No, it isn't. Y is constant. As I compute this area, y doesn't change a bit. So in this integral, treat it like a constant. Every time you see a y, just think k. Literally a constant, because it is literally a constant, as you see in the picture. So that said, this is how we compute that cross-sectional area, and that's really all we needed to proceed. And once you know that cross-sectional area is what you do an integral of as y ranges from start to finish there, and that'll compute that volume for us, the total volume. Yes. Yeah. That's right here. Let me get rid of the mess here. There we go. Okay, so A to B is the range of values of x, and that's just representing that as I'm doing this integral in the x direction, those are literally the starting and ending values of my variable x. And that produces, again, as we claimed, that produces this cross-sectional area here. And that cross-sectional area, why did we care about cross-sectional area? Well, because, as we noted up here, that cross-sectional area is what you're going to multiply by dy in an integral in the y direction to get the total volume. Yeah. Right. Okay. All right. So this is called an iterated integral. The term just a little bugs me just a little bit, but this is the common term to describe this expression. Now, the reason they call it an iterated integral is, you probably noticed, is because it's an integral of an integral. Or said differently, we start with some function, and then we integrate it, and then whatever the result is, you integrate that. It's like you're sort of repeating something. The reason that bugs me is because you're not really repeating the same thing. The first thing you do to it, as I've got it set up here, the very first thing you're doing to this function f is you're computing an x integral of it. And having done that, do you take another x integral? No, you take a y integral. It's a different thing To me, that's not an iteration. It's just semantical. Look, I know I'm just being uptight, right? But it's always bugged me a little bit. I always wanted to call these nested integrals. Because it's literally an integral inside of another integral. That, to me, is the spot on term. But anyway. Okay. Moving along. A couple of things to say about it. First of all, and this is just semantics, but there's a temptation to refer to these integrals as the first integral and the second integral. We have two integrals, one's first and one's second. Here's the problem. Which one should we think of as being first? And here's why I say this is confusing. When we started writing stuff down, the dy integral was the first integral we wrote down. The very first thing we wrote was v is integral dy of cross-sectional area. And then subsequently, we argued, that cross-sectional area, that's computed with this dx integral. So from that point of view, dy is first and dx is second. But when you compute, I can't compute the dy integral until I compute the dx integral. The dx integral is the integrand for the dy integral. I can't start until I know what the integrand is. So you have to compute the dx integral first, and then the dy integral second. So this first and second terminology is hopelessly fraught. And I urge that you not refer to either of these integrals as being the first or the second. There's a lovely way around this, and that is to just refer to this one is the inside integral. That's pretty unambiguous, right? And then likewise, that is the dy in this case is the outside integral. So I think that makes sense. Anyway, that's just anyway, suit yourself. But that's unambiguous. First and second's ambiguous, and we don't know what you mean if you say first or second. Yeah.
Is it possible to have the dy integral inside?
Yeah, that's a great question. Fabulous question. We're going to get to that in a minute. For the moment, I want to let's just stick with what we've got. But great question. That's coming up in 5 minutes. Yeah.
Why would you ever refer to the dy as the first?
Well, yeah, because when you start writing stuff down, that's the very first thing you write down, right? Well, I guess I did it like this. When you're going from start to finish, you're multiplying cross-sectional area times thickness. Then that's an integral in that direction, which for this problem would be in the y direction. So the y integral is kind of the first thing that you sort of write down. Yeah, right. Okay, next little point to consider. Let's see here. By the way, is this the right? Yeah, okay, there we go. Give myself a little bit more space. Don't forget, I know I've said this before, but it's worth repeating. As you're computing this area, you of course have to leave y fixed. You got to decide what value of y you want to know the cross-sectional area for. So while you're computing that cross-sectional area, you got to fix y. So y is a constant. Okay, now let's just think about what the consequences of that are in the algebra. As I compute that area, I am literally computing the inside integral. So said differently then, when you're computing the inside integral, y is constant. That is, the outside variable is constant. Did everybody see that? And it turns out this actually, just a little bit foreshadowing, don't take this too seriously, right? But eventually we will talk about something called triple integrals. And this pattern actually holds for whichever inside integral you might be looking at. There will eventually be three of them. The outside, whichever variable or variables are further to the outside, constants. Treat them in the inside integral, you treat all outside variables as constants. Okay, that's just foreshadowing. We'll come back to that later. Okay, let's do one. Let's get one into the win column here. Here's a reasonable question. I want to compute the volume under a graph. I've got a rectangular domain down here over which I want to compute the volume, and specifically the volume again under, whoops, wrong color, the volume under the graph, which is some surface like that. Let's talk about notation real quick before I go on. This notation that I have for this rectangular domain, the big idea of that notation is that this first interval in that notation represents the range of values of the first variable, in this case x, and the second interval there that represents the range of values of the second variable, in this case y. So that's just a notational shorthand. It's a little confusing because that looks like a cross. It makes it look like we're doing a cross product. That's just not what this is. So just, heads up. Very useful notation though, and I am going to be using that notation significantly, so make sure you know that notation. Okay, all right, so how to do this. Here's a little bit of good news. It's tempting to say that we're going to have to think about cross-sectional areas and what's a constant and what's a, integral in which direction, blah, 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 but we don't, because we've already done that. We've already made this argument, and we've already concluded that volumes are computed by this exact iterated integral. So I'm just going to write that down, citing previous work. And so very first thing we do, here it is. You can see that we have y going from 1 to 2. That's our outside integral. And as I compute individual cross-sections, individual cross-sectional areas, whatever that is, those are integrals as x goes from 0 to 1. Is that cool? Okay. And now it's kind of plug and chug time. Now there's just a couple of things to be careful about here, but it's basically plug and chug time. The first thing to be careful, well here, let me just proceed. So first thing, the antiderivative of x squared. Y'all remember all those formulas. It's 1/3 x cubed. Make sure you know all your antiderivative formulas. Right? It's a heavy prerequisite in this course. We're going to be doing a lot of single variable integrals. So this is the first of many. Okay, so x squared goes to 1/3 x cubed. And here's the first stumbling block. A lot of people will put 1/3 y cubed there. And that's wrong. Because our outside variable is to be treated as a constant. That means this y squared is a constant. And the antiderivative of a constant is constant times the variable. And our variable is x, so it is x y squared. Is that cool? Lots of students mess this up. So heads up, this is part of your job as you're computing an iterated integral is to consciously, right? Don't assume that you're going to keep track of this sort of by instinct, right? You have to consciously make a point of thinking, okay, while I'm doing the inside integral, okay, I'm doing the inside integral, that means the outside variable is constant, so y, everywhere I see a y in here, I've got to remember that y is to be dealt with as a constant because it is literally a constant. Right? So heads up, that again, part of your job in doing these integrals. Everybody good on that? Okay. All right, here's the second stumbling block, and this is, you see this a lot. I see this a lot. As you're computing this inside integral, you do the antiderivative, you take the bounds, let's see, our bounds here are 0 and 1, so you got your 0 and your 1, and then you start plugging this stuff in, so you're going to take that value of 1, you're going to plug it in, and here's the whoopsie. A lot of students will plug it in for y also. because it looks like a variable. And we're plugging in for the variables. Right? And you can see the temptation. It's easy to do this little whoopsie. Okay, so my workaround, this is just me. You've already noticed as I have it written, but I don't just write down these numbers 0 and 1 and leave it, because I've done this too. I've messed this up too, because it's so easy. I like to write down as a reminder to myself, just to prevent the dummy move that I can't. Oh my God, it's so hard to stop. Write x equals 1. And then when you find yourself thinking, hey, should I plug x equals 1 in for y? Then why would you do that? That doesn't make any sense at all. And so having this written here, I think, will prevent you from putting it where it doesn't belong. Does that make sense? Okay. This is not a requirement of the course, but this is strongly urged advice, right, that I think you'll find well worth the second and a half that it'll take you to write that down, right? Well worth that second and a half. Okay. All right. Okay, so let's see here. Whoops, back down to here. So everything else is plug and chug, and make sure you can do the rest of this. It's all, again, it's all plug and chug, but make sure you're good with that. So think through all the details there. It's just really a matter of doing single variable calculus at that point. Okay. All right, somebody asked, can you do them in the other order? And yes, absolutely. And there's an argument to be made there. And this is a fabulous little exercise for everybody to do on their own at some point, which is just think through the argument. If you were to instead, from the very beginning, instead of taking slices, instead of taking slices perpendicular to the y-axis, let's go the other way. And instead, think about what would happen if you made slices perpendicular to the x-axis. And you'd have little you could take a loaf of bread and you can slice it the other way, Some people like to do that and get big long sandwiches, there's something said for that. So that's all this is, right? We're just going to take, instead of slicing perpendicular, we just slice perpendicular to x. And then ask yourself, how would I compute that cross-sectional area? That cross-sectional area is the area under a curve this way, which means y is the inside variable. Right? And then x, of course, is the outside variable. So anyway, if you draw the picture analogous to this and compute that cross-sectional area analogous to this, and just everything's going to be a little bit different. What you're going to find is that the effective punchline is that you just switch the order of the differentials and the bounds. So what had been your outside bounds, y going from C to D, now are your inside bounds, y going from C to D. And what had been your inside bounds, x going from A to B, now are your outside bounds, x going from A to B. So yes, and geometrically, when you switch your bounds and your differentials, all you're doing is slicing the other direction. So again, this is a good exercise. I want everyone to take a crack at this. I think I wrote that. Yeah. So think through these details, right? Specifically, doing it that way. And this is what you get. Last little warning: do be careful when you. So here's your bounds and here's your differentials. It's easy whoopsie to just switch the differentials, and that doesn't make any sense. You have to switch the bounds with the differentials, because after all, what are C and D? Those specifically represent values of y. whether you're doing your Y slicing first or your Y slicing second, whatever, those C and D are Y values. And it only makes sense then for them to be connected in an interval to the Y differential. So you got to be careful with that. Okay. Oh yeah, and then I have a warning here. This is going to be a mysterious warning for the moment. I say this only works if the domain is a rectangle, and you might reasonably complain. That was the whole question. The whole question here was, how do we compute the volume under a graph sitting over a rectangle, right? So, what do you mean this only works when you're looking at a rectangle? Well, it's going to turn out, it's going to happen pretty soon, possibly today, kind of betting against it at this point, but certainly tomorrow, we're going to entertain a question just like this, but without assuming that your domain is a rectangle. And when we get to that non-rectangular domains, this business here about just, you can just switch. For non-rectangular domains, it does not work. This is peculiarly just for rectangles. And everything changes when you get non-rectangle domains. Okay, so now let me make a tempting statement that's going to turn out to be very wrong. Tempting statement, though. Going back to single variable calculus. Well, let's see. I guess I don't really have this written down anywhere. But okay, so let me just leave it here. In single variable calculus, first example you always see is area under a curve. Draw the various pictures and Riemann sums and all that business. And then you have this construction called an integral, and then various other questions come up, like how would I compute, the mass of a rod where the mass per unit length is dependent on position. You all have seen these kinds of examples. They're early on examples in single variable calculus classes. And awesomely, same construction works, right? The exact same construction that we use to compute the area under a curve will compute the mass of a rod, and it'll compute the number of bacteria in your petri dish, and it'll compute a bazillion examples, all with the exact same construction. So we speculate maybe the same good news happens here. Maybe this same construction that I use to compute the volume under a graph surface, maybe I can use the same construction to compute the mass of not a rectangular rod, but of a two-dimensional rectangular sheet where mass is distributed over this two-dimensional sheet, and therefore the corresponding density mass per unit area. Kind of a two-dimensional analog, a one-dimension up analog of the old Calc 1 problem. And it's tempting to say, okay, well then, boom, same construction ought to work. You just put the density where the height was, and feels like it ought to work. And I assume you all see the temptation here. I mean, it did in single variable, why wouldn't it in multivariable? And here's the bad news. This argument does not make any sense. It doesn't make any sense. This is a problem. It's a very serious problem, as follows. Now, let's think about what we've already done in the construction we just got through talking about. I found myself looking at that, which is height, being multiplied by that, which is length, and very reasonably I argue that height times length gives me area. And here's where that is in the picture. Let's go back right to it. Here it is. You know what? I need here we go. This area I compute as a height which is the value of the function. So height times, I forgot what color I used. Shoot, it doesn't matter. This thickness, which is dx, and so this is literally computing that little strip of area right there. And there's the picture, and that's the area as a thing that I can point to, and I can see it, and I understand what area is, because we have intuition for area, and I've used area a million times. And I furthermore know, by the way, that area combined with all of the other analogously computed areas gives me the whole area. This is what we call the feature of accumulation. The whole is the sum of the parts. How do I know the whole is the sum of the parts? Because there it is. I can see it. It's right there. I can imagine this area being made out of cardboard, and I have a pair of scissors, and when you cut up cardboard with scissors, the area doesn't disappear. The whole is the sum of the parts is just geometrically obvious. Okay, now let's think that through, that aspect of the calculation. Let's think that through for our new scenario here. I've got that, which is mass per unit area, and I'm multiplying by length. And what do you get when you multiply mass per unit area times length? In other words, what is this thing that I'm allegedly doing an integral of? I don't know what that is. That's not a thing. At least not obviously. Mass per unit area, the deal with mass per unit area is that this is something that if you multiply it by area, then will give me mass. That's its job, right? Its job is you multiply by area, you get mass. I don't know what happens when you multiply it by length, and I don't know what happens when you multiply it by work either. So, dead in the water, right? The very first thing that we need to write down in the hopes of being able to maybe eventually possibly compute mass, this very first thing we write down, I don't even know what that is. And you can't make an argument about something if you don't even know what it is. Everybody see the problem? This is a nasty, deep, fundamental problem in this approach. We are up a creek without a paddle. And we lose. There is no happy ending to this story. You just can't finish that argument. Okay. There is a different way to answer these kinds of questions, but we have to completely abandon this iterated integral approach. The iterated integral approach really only makes sense to compute volumes, because it's the only one where I can kind of take this mismatch of type and actually make sense out of it geometrically. Yeah.
So are we considering a rectangular sheet in 3 dimensions?
No, in 2 dimensions. Yeah, just so you imagine a 2-dimensional area, right? And it's kind of like in single variable calculus. You can compute. We like to think of an integral, from A to B. We like to think of it as computing an area because, that's one of the applications that it will do, right? But if the question is, I have a bunch of mass distributed across this 1-dimensional rod, then there is no area in the problem. It's just a 1-dimensional rod, and mass per unit length makes sense on the rod itself, and it's an intrinsically 1-dimensional problem. And you can think of it in terms of a graph if that makes you feel better. But here, analogously, if you're computing volume, then the question looks 3-dimensional. But if you're just trying to add up mass distributed over an area, there is no reason to look at volume. There is no volume in the question. The question's intrinsically two-dimensional. And so it's just a rectangle in the plane. Is that cool? Yeah. Okay, so we reached a dead end. We're going to come back and fix that, but we do have to start all over in some sense. We're going to define a new construction called a double integral. You'll notice as we were doing this stuff, I didn't say the word, no worries. I didn't say the word double integral anywhere. These are not double integrals. Right? These are iterated integrals. So now we're going to have to create a new thing called the double integral. Now to do that, I do want to real quick flashback to single variable integrals. Single variable integrals are Riemann sums. So this definition here, very important. Single variable integrals are Riemann sums. That's the definition for a bunch of really good reasons. Ultimately, and I know that that's not how y'all tend to think about single variable integrals. Very few people at this stage are sold on thinking of it in terms of Riemann sums. A lot of people misunderstand the purpose of Riemann sums. I kind of had the false impression when I was y'all's age, when I was in a single variable calculus class, that this was the outdated construction that got obviated when Newton thought of calculus. That this is just that's the old clunky old style way to compute the area under a curve, and that no one would ever touch that ever again once calculus is an option. That's just kind of the way it was presented to me. That's the impression anyway that I was left with, and that's wildly false. For one thing, Riemann wasn't even alive yet when Newton did calculus. It was like 100 years later, 150 years, I forget the exact date, but this is not the outdated, obviated tool. So this is a topic that I could spend a lot of time on, and I have to exercise some self-control here. I do have on my YouTube channel, in the miscellaneous topics playlist, several topics there that I think are relevant to all students who come in to take Math 212 or Math 219. Things that should have been emphasized in earlier courses, but that historically it just seems anyway that these days that just aren't. And one of them is about integrals and what's an integral. And so why Riemann sums are important is I discuss at length in that video. And if you're not 100% sure that you know why, if you're not anyway, very likely most of you should take a look at that video, and it's only like 30 minutes or something. And really only it's the first 20 minutes that you really need to watch. But I encourage everybody to give that a look. Here's the short version. This idea of thinking of integrals as representing area is not, that's fundamentally not right. That is one of many applications and not a particularly useful one. Be blunt about it. The great majority of applications have nothing to do with area. We've already talked about one. If you want to compute the mass of a one-dimensional rod, well, you write it as a Riemann sum, you compute with the fundamental theorem of calculus. Area doesn't come up. There's no area in the question. There's no area needed for the solution. It's got nothing to do with it. Right? Now, what you'll see very often, and I'm going to try to be as quick as I can on this. Watch the video if you want to see the detailed discussion of this. What very often happens in single variable calculus classes is someone will say, you want to compute the mass of a one-dimensional rod? Okay, well, first of all, I'll claim that's an area, at which point I'm like, wait, what? You said it was a one-dimensional rod. What area? What are you talking about? Where's the area? Why are you're telling me mass is area? Persuade me, please. Why is mass equal to some area? Right? And then they happily sort of, go on with the computation. But I'm just like, what? Why? Where did this area come from? Now, if you really press, a Calc 1 teacher on this, they will make an argument that I'm going to call kind of just next door to making a Riemann sum argument. And then, having persuaded me that mass, I can think of it as an area, they'll say, and that area is something we can compute as an integral with the fundamental theorem of calculus. At which point I counter, okay, well, why didn't we just do this? Right? What purpose did that little jaunt into discussing area, what purpose does that serve? It doesn't. Right? It's kind of a crutch. I mean, my honest opinion is I think a lot of single variable calculus teachers don't really understand Riemann sums. And that this is the way they avoid Riemann sums. And that's really unfortunate. Right? I'm not blaming any individual instructors, but I think that is a thing. That's not unheard of. Okay. Anyway, very importantly, integrals are Riemann sums. Riemann sums are the construction that we can get to by as we entertain various applications. So if you want to compute the amount of work it takes to perform a task, break that task up into little pieces. Each individual piece, you can write down an expression, you add them up, you've got a Riemann sum. Area not necessary. And once you have a Riemann sum, aka an integral, then you compute with the fundamental theorem. And that's the case for the great majority of applications. Okay, I think I've already talked too much about this, so let me just proceed along. So when we find ourselves looking to generalize the idea of an integral, I want to now come up with some meaningful way to talk about a double integral, a two-dimensional analog of an integral. Let's not lose sight of the fact that this is what integrals are. Integrals are Riemann sums. This is what we need to generalize. We've got to generalize the idea of a Riemann sum. So instead of an interval that I'm going to chop up into little pieces, well, let's see here. I guess I'm in two dimensions now, so I guess I'm going to want to look at an area that I'm going to want to chop up into little pieces. And this is what that looks like right here. When you take an interval and chop it up into little pieces and add up over all those pieces, you get this expression. Notice that on each piece, on each little piece, you're going to be multiplying, let's see here, some integrand for some purpose times the size of that piece, namely the length of that little piece, called delta x. Well, the two-dimensional analog of that is that we take an area, and then on each little piece, now a piece of area, not a piece of length, now that's a piece of area. For whatever reason, I'm going to want to multiply that. We'll figure out why we would want to do such a thing later, but I'm going to want to multiply some integrand for some reason times the size of that piece, just like delta x was the size in this context was length. Well, in this context, the size, it's an area, so the size is the area, which is delta x times delta y. Everybody see how that's kind of the analogous thing? So, the copycatting in mind, that's where the definition of an integral is going to come from. I'm just going to literally take this expression right here and say, yeah, that's kind of the analog, the two-dimensional analog of a single variable integral. So this is what we call a double integral. This is the notation that we're going to use. I think the notation is pretty satisfying, and let me get rid of the junk, in the sense that this is just a shorthand for representing that little piece of area. And this, let's see here, this right here is just a representation of that, I'm adding up in the limit as n goes to infinity as we slice finer and finer. But I'm going to use two integral symbols because you'll notice that we're adding up both in the x direction and also in the y direction. We're adding up into two different directions because there's a lot more pieces, right? There's, if you will, there's kind of in pieces to add up here. Literally, I goes from 1 to n. There's in different pieces. Here, I'm slicing it in two different directions. There are literally in squared pieces here, and so double equal. So that's just terminology and notation. This is going to be bonkers useful, and we're kind of out of time, so I'll just draw the line right here. The book spends a bit of time using irregular partitions and test points, and y'all may have seen analogs of this in Calc 1 classes, and it has its purposes, and that's really good math, and if this were a math major class, we would get real upset about all that kind of stuff, and it would be important, but that's not what this class is, so y'all are not responsible for that stuff. That's noted on the content syllabus. And the justification I'm going to give you is that when your integrand is continuous, they don't matter anyway. So for computational purposes, in the great majority of cases, it's nothing to worry about. Okay, drawing the line right here. We'll pick up here tomorrow. Y'all have a good rest of your Monday. See you later.